So we're going to start looking at some of the common organic chemistry reactions that are similar to the types of reactions that we're going to actually see when we start talking about biochemistry. So it's a good idea to be able to recognize these and recognize how these things change over time here. So some of the 5 types of reactions that we're going to look at here are the elimination reaction, substitution reaction, combustion reaction, addition reaction, and rearrangement. So I like to say, there's a goofy little saying here, see the S car go, E-S-C-A-R, S car go. So this is just a way to kind of remember the names for the different types of reactions. Here's the first one, the elimination reaction. And we can tell it's an elimination reaction because we start off with only one reactant. So in this case, we have ethanol, and then the products, we have 2 reactants. So something has been eliminated from that longer chain compound, and that in this case is water. So we have an elimination reaction. That's the first type. The second type is a substitution reaction. And this is where we start with 2 compounds, and then we end up with 2 compounds, but some of those functional groups have swapped out from one group to another. So we've substituted groups there. The third type is a combustion reaction. And this is a reaction that ultimately is what our metabolism is, the breakdown of our food. We're going to make carbon dioxide, water, and energy. In this case, if it's a organic chemistry combustion reaction, there's generally heat. If it's happening in our body, that heat is generally considered to be some type of useful chemical energy that's made instead. So this is a combustion reaction. And then we have an addition reaction, basically the opposite of the elimination reaction, where we start off with 2 compounds and then we end up with 1. So here you can see these hydrogen molecule is added to that double bond region, and then we have those combining to form ethane, so that alkane product. We also have a rearrangement reaction where there's just 1 reactant and 1 product. And the thing that changes here is that where the functional groups are found have been reorganized and rearranged. So as you can see here on this product, the reactant on the left, we have this methyl substituent group and this methyl group here outside of this double bond. So this is cis, it's a cis butene, same side of the functional group, or on the same side of this double bond. And here we have this methyl group on the opposite side, which makes it trans. And so you can see the molecular structure hasn't changed at all, or the molecular, right, the molecule, if we just had the carbons and the hydrogens and look at that, it's right C1, 2, 3, 4, and then H6, 7, 8. So C4H8. That's the same as on the right end as it is on the left, except for there's been a rearrangement of where these functional groups or those side chain groups go. So this is just a rearrangement reaction. So we're going to kind of go over some of the differences between organic reactions and biochemical reactions, but let's just first look at this reaction here with these double bonded carbons and this water molecule. This is called a hydration reaction when we get this water to combine with that double bond. So what kind of reaction is this? It's called a hydration reaction, but if you think about what this actually would be called, it would be the addition reaction, right? So we're adding 2 things together. It's the opposite of an elimination reaction. When we were talking about this in organic chemistry, we spoke about Markovnikov's rule. So if we're going to do addition reactions on double bonds, generally the more substituted carbon, so it's the carbon with more other carbons or other bulkier groups, that's going to be the carbon that's going to get the carbocation, and that's generally where the more electronegative element is going to go. For example, bromine or the oxygen in the water molecule in that last case. So the more substituted carbon, so that's this carbon right here, right? That carbocation is going to be more stable, and that's why that bromine is ultimately going to bond to that carbon. So again, when we have those partial positives, partial negative charges, this is going to force this type of final product, and that's called Markovnikov's rule, if you recall. So again, if we're going to think about this just like hydrogen bromide, practice doing this with hydrogen chloride or water, for example. I want you to redo this reaction with water and tell me where that hydroxide is going to go, this OH is going to go, versus where the hydroxide is going to go. So write that down, pause this, and then we'll move forward. So what's going to actually happen is normally for organic chemistry compounds, in the we usually have some type of catalyst here to help activate this reaction. But we're going to have Markovnikov's rule dictates that more substituted carbon is going to get the bulkier group or the more electronegative group within that addition reaction. So this is going to be the 2-methyl-2-propanol is what we're going to get in the end. But we're actually, in biochemical reactions, none of this matters really, what is more favorable or not under general conditions, because we have enzymes. The enzymes are going to dictate the final outcome. So all of this is a kind of null and void. We don't need to worry about this in biochemistry because we don't use just chemicals here. We're actually using enzymes, and that's going to dictate whether the hydroxide adds here or if the hydroxide adds to that other. So what I want you to do is look at these 3 different chemical reactions. I want you to define if they're elimination, substitution, combustion, addition, or rearrangement. So please pause and do this. This is going to be, again, helpful if you're just listening to me tell you the answers. It's not really valuable for your learning. So please pause, think about these, and then unpause and see if you were right. This top one, A, is going to be an addition reaction, obviously, right? Addition reaction, because we have 2 reactants and 1 final product. So we've added these together. And here we have 1 reactant and 2 products. So that's going to be the opposite. It's going to be an elimination reaction. And finally, on the bottom, we start with 2 reactants, end with 2 products. And we've basically substituted that chlorine and that hydroxide right over here. And so that's going to be a substitution reaction. What I'd like you to do now is I'd like you to do another kind of activity. So pause this and work on these things. What I'd like you to do is draw structures for both the cis and trans isomers of 2-hexene. So start off with the 2-hexene molecule and pause this, and then what I'd like you to do is tell me what the structures are for the condensed structure. I'd like you to draw out the atoms attached to the double bonded carbon, and then I want you to look at and attach, make sure that you're able to attach both different groups in the different positions for both cis and trans. This is basically how we can walk through doing that, where we first have to draw the hexene, so methyl ethyl propyl butyl pentyl hex. So that's going to be a 6-carbon chain. On that second carbon from the end, 1, 2, we're going to have a double bond because that's hexene. And then we know along that double bond, we can have the bulkier carbon chain go up or down, and that's going to dictate if it's a cis or a trans compound. So now we're going to start talking about a little bit more about aromatic compounds. And you can see here the big thing about aromatic compounds, or they're unique, is because they have these pi electrons, right? These double bonds are really those electrons in a different plane kind of above those carbons. You'll also notice these carbons are kind of flat, and that's because of those electrons that are floating above and below. It's not crinkled up like they are in glucose or in 6-chained rings that don't have double bonds in them. Produces this ability for these electrons to flow around this ring in these different electron formations, gives it some stability. So generally, benzene rings, for example, with hydrogen or bromine or hydrochloric acid or acids, they're not going to have addition reactions because that would influence and disrupt this very stable ring. To know for Huckel's rule that how we can figure that out is if we have basically these every other. So if we have every other carbon has a double bond to it, we can't have it on every single bond, otherwise that doesn't work. But we have to have a conjugated system where we have unhybridized p orbitals here on every other carbon. And also it has to follow Huckel's rule, which is 4n plus 2 pi electrons. So what that means is that n number, remember, can equal any whole number. So for example, 1. So if we had this n, it can be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And basically that 4n, so if we have 1 times 4 is 4, plus 2 is 6 total pi electrons. You'll notice up in this we have 2, 4, 6 pi electrons up here. I'll highlight these in blue, right? We have 2 in this bond, 2 in this bond, and 2 over here in this bond. So we have 6 pi electrons. That follows Huckel's rule, and that tells us, Huckel's rule tells us if this is a conjugated aromatic compound. So it must be conjugated, it must be in a ring like this is, and it also has to follow this number of pi electrons. So here when we're looking at aromatic compounds, we have, when benzene is a substituent, that group's called a phenyl group. So when this is off of some longer chain, then this is called a phenyl group, just so you're aware.